100 milligrams of uranium-238 are stored in the container. If the half-life of uranium-238 is known to be 4.47 billion years, how many years will it take for only 10 milligrams to remain in the container? Now, we should identify right away that we're dealing with exponential decay in this problem, because we're investigating a substance that is, for lack of a different term, decaying. It's decomposing, and we want to know how quickly. So we're given several key pieces of information, and we also know our exponential decay formula, which will come in handy. The formula, f of x equals a times e to the negative k times t, has a as our initial value, k as the constant rate of decay, and t in time. So we're told that the half-life of uranium-238 is 4.47 billion years. So what that tells us, that exactly half, or 0.5a, of our initial substance will remain after 4.47 billion years. I should note that at this time, instead of writing out 4,407,000,000, I'm just going to write 4.47 so that we can keep it somewhat condensed for solving. Looking at our equation, we notice that we can divide both sides by a, and we have 0.5 equal to e raised to our unknown constant times 4.47 billion. Since we're trying to solve for k, and e is the base, it would be a good idea to take the natural logarithm of both sides. Now we know by the power property of logarithms that this exponent can be moved down to be a constant multiplied out front. So now we're left with the natural log of 0.5 equal to negative k times 4.47, our former exponent, times the natural log of e. However, we know this to be equal to 1, so what we really have is the natural log of 0.5 equal to negative k times 4.47 billion. I used my calculator to estimate the natural log of 0.5 being approximately equal to negative 0.6931. The only step remaining is to divide both sides by our time. And like I said before, we were just using that 4.47 to really just signify we knew what time it was. Now, when we divide, we're going to divide by that 4,470,000,000 so that we get the most accurate answers. I also completed that calculation on my calculator just now, and actually divided by the negative 1 while I was at it. So I found my k value to be equal to 1.551 times 10 to the negative 10 power. Our k value we found to be exceptionally small, but that's okay. Now this has been step 1 of this problem. Please see the next podcast to figure out how we determine how many years 10 milligrams will be left.